Tonight, we're taking a slow journey through the history of C++, one of the most influential programming languages ever created. From its humble beginnings in the early 1980s, to powering everything from operating systems and video games, to financial software and spacecraft, C++ has quietly shaped the modern digital world. So get comfortable, dim the lights, and let your mind relax. There won't be any quizzes or complicated code to remember tonight. Just a gentle story about the people, ideas, and milestones that turned C++ into a language trusted by millions of developers around the world. Our story begins in 1979 in a research building in Murray Hill, New Jersey, at a place called Bell Labs. Bell Labs was one of the most important research institutions in the entire history of technology. It was the birthplace of the transistor, the laser, the Unix operating system, and countless other inventions that shaped the modern world. And it was here, in this quiet, intellectually rich environment, that a young Danish computer scientist named Bjarne Stroustrup arrived to begin a new chapter of his career. Bjarne Stroustrup had just finished his PhD at Cambridge University in England, where he had been working on distributed systems. Before that, he studied at Aarhus University in Denmark, earning a degree in mathematics and computer science. While he was a student in Denmark, he was introduced to a programming language called Simula, specifically a version known as Simula 67, and this language would end up changing the course of his life, and in turn, the course of software history. It is worth resting for a moment on what Aarhus itself was like in those years. A quiet Danish university town, with a small but unusually serious computer science community gathered around it. Christian Nygaard, one of the two original creators of Simula, was a frequent visitor to Aarhus during Stroustrup's student years, and Stroustrup later credited those visits with shaping how deeply and how early he came to understand the underlying philosophy of object-oriented thinking, not simply as a set of syntax rules to memorize, but as a genuinely different way of organizing one's thoughts about a piece of software before a single line of code is ever written. This distinction between learning a language's surface features and absorbing the deeper philosophy underneath it would matter enormously later, when Stroustrup set out not merely to copy Simula's features, but to translate its underlying spirit into an entirely different kind of language. Simula was unusual for its time. It allowed programmers to organize their code around the idea of objects, little self-contained units that bundled together data and behavior. This idea is called object-oriented programming, and at the time, it was still a fairly obscure academic concept. Stroustrup found this way of thinking about programs to be elegant. It matched the way he thought about real-world systems, with their many interacting parts. But there was a problem. Simula was slow, painfully slow, for the kind of large-scale, performance-sensitive systems work that Stroustrup wanted to do. It was a language built for clarity and simulation, not for raw speed. At the same time, Stroustrup also had exposure to a language called BCPL, which stood for Basic Combined Programming Language. BCPL was about as different from Simula as you could imagine. It was fast, low-level, and close to the hardware, but it offered almost none of the organizational tools that made Simula pleasant to write large programs in. It had no concept of types in the way modern languages do, no classes, no objects, nothing to help a programmer manage complexity as a project grew larger. It can help to imagine these two languages almost as two different personalities. Simula was thoughtful, patient, and beautifully organized, the kind of careful, deliberate thinker who plans everything out before acting, but who sometimes moves a little too slowly for urgent, practical work. BCPL, by contrast, was quick, blunt, and efficient, someone who gets things done immediately and without fuss, but who can leave a mess behind if a project grows too large or too many people need to collaborate on it at once. Stroustrup, quietly, patiently, began to wonder whether these two very different temperaments could somehow be combined into one. So Stroustrup found himself caught between two worlds. One language was expressive but slow, the other was fast but bare bones. He wanted something that combined the best of both. When he joined Bell Labs in 1979, he was given a problem to think about, involving the Unix operating system and how to analyze it for distributed computing purposes. And as he thought about how to tackle that problem, he kept returning to the same idea. What if you could take a language that was already known for being fast and portable and add to it the organizational power of similar-style classes. The language he chose as his starting point was C. C had been created earlier in the 1970s by Dennis Ritchie, also at Bell Labs, as a system programming language designed to work hand-in-hand with the Unix operating system. C was already beloved by systems programmers for being lean, efficient, and very close to the underlying hardware, while still being more readable and portable than writing in raw assembly language. Unix itself had been rewritten in C, which gave the language enormous credibility and reach, since Unix was spreading rapidly through universities, research labs, and growing technology companies throughout the 1970s. C was fast because it did not hide much from the programmer. It let you work directly with memory addresses, manipulate bytes, and avoid the kind of overhead found in higher-level, more abstract languages. But this same closeness to the hardware made it harder to use for very large, complex software projects, the kind that might have hundreds of thousands of lines of code, written by many different programmers over many years. There was no built-in way to bundle related data and functions together cleanly, no strong support for the kind of abstraction that helps teams manage growing complexity. It is worth pausing, gently, to appreciate just how deliberately Stroustrup chose C, rather than starting something entirely new from a blank page. He could, in principle, have invented a completely fresh language with no obligation at all to look or feel anything like an existing tool. But he recognized something quietly important, that a brand new language with no ties to anything familiar would face an enormous, uphill struggle for adoption, no matter how elegant its design might be. By choosing to build directly on top of C, he was making a calculated, practical bet that the easiest path toward wide adoption was not to ask the world's programmers to abandon everything they already knew, but instead to offer them a careful, gradual extension of a tool they already trusted and already used every day. So in October of 1979, Stroustrup began building something new. He started with what he called a preprocessor, a kind of translation tool that would sit in front of the regular C compiler. This tool was named CPre, short for C preprocessor. CPre allowed programmers to write in an extended dialect of C that included some similar-inspired features, and then CPre would translate that extended code back down into ordinary C, which could then be compiled and run using existing C compilers. This approach meant Stroustrup did not need to build an entire compiler from scratch. He could borrow all of the existing tools, all of the existing compilers, all of the existing libraries that already worked with C, and simply add a translation layer on top. By March of 1980, this early tool had been refined enough that it was being used for one real software project and several smaller experiments. Inside Bell Labs, Stroustrup later recalled that his records showed the preprocessor in use on around 16 different computer systems by that point, which for an early, experimental, internally distributed tool was a meaningful sign that other engineers found it useful. It is worth sitting quietly with just how modest this beginning truly was. There was no grand announcement, no public unveiling, no press release of any kind. There was simply a researcher, working largely on his own, refining a small internal tool, sharing it quietly with a handful of colleagues who might find it useful for their own particular projects. So much of the history of important software begins this way, not with a dramatic launch, but with a slow, patient, almost invisible accumulation of small, practical improvements, tested quietly against real problems, one careful step at a time. The language that this preprocessor supported came to be called C, with classes. The name describes exactly what it was, ordinary C, but extended with the concept of classes, which is the central idea borrowed from Simula. A class lets a programmer define a new kind of data type that bundles together variables, which represent the state or properties of something, with functions which represent the behaviors or actions associated with that thing. So instead of having scattered variables and separate functions that loosely operate on them, a programmer working in C with classes could define a single coherent unit representing, say, a bank account, or a network connection, or a shape on a screen, with its own internal data and its own associated operations, all bundled neatly together. Several other important ideas as well. It brought basic inheritance, which is a way for one class to be built as an extension of another class, inheriting its properties and behaviors, while adding or modifying some of its own. This mirrors how, in the real world, A specific category of thing can be thought of as a more specialized version of a broader category. It also introduced inlining, a performance technique that lets the compiler insert the actual code of a small function directly at the place where it is called, avoiding some of the overhead of a traditional function call. It introduced default function arguments, allowing a function to be called without specifying every single parameter, with sensible defaults filling in the gaps. And critically, it brought stronger type checking than plain C offered, which helps catch certain kinds of programming mistakes earlier, before a program is even run. An early description of C with classes was written up as a Bell Labs technical report in April of 1980. This was followed by a more polished and widely read paper, published in a CM Sigaplan, Notices in April of 1982, and later by a more detailed Bell Labs technical report. The title of one of these papers was Adding Classes to the Key Language, an exercise in language evolution, which captures quite well how Stroustrup himself viewed the project at the time. It was not yet imagined as an entirely new, freestanding language with its own grand ambitions. It was conceived more modestly, as a natural evolution of an existing, trusted tool. It is interesting, too, to notice the careful, almost understated language Stroustrup chose in titling that paper, calling it an exercise in language evolution rather than something more sweeping or self-important. This kind of quiet, modest framing recurs throughout much of Stroustrup's writing across the decades. He was, by most accounts and by his own description, a careful, deliberate engineer first, someone who preferred demonstrating that a feature genuinely worked, in real, practical use, before publicly describing it, rather than announcing ambitious plans and working backward from there. This disposition, cautious, grounded, oriented toward what already works, rather than what merely sounds appealing, would go on to shape the entire subsequent culture of how this language's community approached new ideas for many decades afterward. But as more engineers inside Bell Labs began experimenting with classes, Stroustrup started to notice the limits of the preprocessor approach. Translating extended syntax into plain C before compiling worked for a while, but it became increasingly difficult to add more sophisticated features this way. Some of the capabilities he wanted to introduce simply could not be expressed cleanly as a simple text transformation feeding into an unmodified D compiler. The preprocessor model was a clever bridge, but it was starting to creak under the weight of his ambitions. So in 1982, Stroustrup began designing a more thorough successor. Rather than relying on a lightweight preprocessor, he began building what is called a proper compiler front-end, a piece of software that would more deeply understand the new language's structure and translate it into C, but with much more sophistication than the earlier CPRE tool allowed. This new compiler was named C-Front, short for C front-end. C-Front would take source code written in this evolving language and translate it into standard C code, which could then be compiled using any ordinary C compiler available on a given system. This design decision, to have C-Front output portable code rather than directly producing machine code itself, was hugely consequential and quite clever. It meant that wherever a C compiler already existed, which by the early 1980s was an enormous number of computer systems thanks to the spread of Unix, this new language could also run, almost immediately, without needing entirely new compiler infrastructure, built from the ground up for every different kind of computer. It was a strategy that prioritized portability and practical adoption over architectural purity, and it would prove to be one of the most important factors in the language's early success. Stroustrup designed and implemented C-Front between the spring of 1982 and the summer of 1983. During this period, the language grew substantially beyond what C with classes had offered. New features were added that would become deeply, permanently associated with this language's identity. Among the most significant was the introduction of virtual functions, a mechanism that allows different classes, related through inheritance, to each provide their own specific version of a shared function, with the correct version automatically selected at the moment the program actually runs, depending on the real type of the object involved. This idea, sometimes called polymorphism, is one of the conceptual pillars of object-oriented programming, and it gave programmers a powerful new way to write flexible, extensible code. Alongside virtual functions came function overloading, the ability to define multiple functions that share the same name but differ in the kinds of inputs they accept. letting the compiler automatically choose the correct version based on context. This might sound like a small convenience, but it meaningfully changes how naturally code can read, allowing operations that conceptually do the same kind of thing to share an intuitive, consistent name, regardless of the underlying data type involved. The language also gained references, indicated by the ampersand symbol, which provide an alternative, often gentler way of working with the memory address of a variable, compared to the raw pointers inherited from C. References would go on to simplify a great deal of everyday programming, making certain operations less error-prone and more readable. Another addition was the const keyword, which lets a programmer explicitly mark certain data as something that should never be changed once it is set. This might initially sound like a restriction, but in large software projects, restrictions like this are often exactly what helps prevent subtle, hard-to-track-down bugs. By telling the compiler and other programmers reading the code that a particular piece of data is meant to be read only, the language could catch accidental modifications before they ever caused a problem. A much smaller but surprisingly influential addition was the introduction of single-line comments using 2 consecutive forward slashes. This particular convenience was borrowed directly from BCPL, the very language that had originally inspired Stroustrup, alongside Simula. This small piece of syntax, the double forward slash for marking a quick note within source code, would go on to be adopted by an enormous number of later programming languages, far beyond this one, becoming one of the most universally recognized little symbols in all of software development. It was also around this period, in 1983, that the language received its lasting name. For a brief stretch, it had even been informally called C84, a placeholder referencing the year. But ultimately, a colleague at Bell Labs named Rick Masiti suggested the name that would stick, and which we still use today. The name took the symbol from the increment operator in C, the double plus sign, which in the C language is used to mean increase a value by 1. By attaching that symbol to the letter C, the new name suggested an enhanced, incremented version of C itself, a clever, slightly playful nod to where this language had come from and what it was meant to be, an evolution, an increment, a step forward from C. It is a small detail, but a charming one, that the language's permanent name did not emerge from Stroustrup himself, the person who had designed and built it from the very beginning, but instead from a colleague suggesting a playful pun based on a small piece of syntax that every C programmer already knew by heart. There is something quietly fitting about that, a name born not from a marketing meeting or a carefully workshopped branding exercise, but from the easy, informal, slightly joking conversation of engineers working closely together in the same research department, all of them already fluent in the small grammatical habits of the C language, and able to appreciate the little joke embedded in the name almost instantly. In 1984, Stroustrup implemented something that would become deeply woven into how generations of programmers would interact with this new language: the first stream input and output library. This provided a way for programs to read information in from a user, or print information out to a screen, using a notation built around an output operator, rather than a simple, traditionally named function call. The idea of using an operator this way for output was actually suggested to Stroustrup by Doug McIlroy, a colleague at Bell Labs who, interestingly, had also been the person who originally suggested the influential concept of Unix pipes, the mechanism that lets small Unix programs be chained together so the output of one feeds directly into the input of another. It is a nice, quiet thread connecting 2 foundational ideas in computing history, even though they might seem unrelated at first glance. The very first C++ language reference manual was published internally at Bell Labs in 1984, formalizing much of what the language had grown into by that point. And then, in 1985, 2 enormously important things happened, almost simultaneously, that would set this language on its path toward becoming one of the most widely used programming languages in the history of computing. First, the language was released commercially. This meant that, for the first time, organizations and individuals outside of Bell Labs could obtain and legally use the compiler and its accompanying foundational libraries. For non-commercial use, the cost was kept deliberately low, around $75, covering essentially just the cost of physically shipping the materials, since widespread internet access, as we think of it today, simply did not exist yet. This was an era when software distribution often meant tapes or discs mailed through the postal service, accompanied by thick printed manuals. Second, and just as significant, Stroustrup published a book titled The C++ Programming Language. This book would go on to become the definitive reference for the language for many years to come, and this mattered enormously, because at this point in time, there was still no official, independent standard defining exactly how the language should behave. There was no committee, no formal specification document in the way many established programming languages eventually receive. Stroustrup's book itself functioned as the de facto standard, the central reference that compiler implementers and programmers around the world turned to when they needed to understand precisely how some feature of the language was supposed to work. It is worth dwelling for a moment on what an unusual position this placed Stroustrup in, professionally and personally. For a number of years, the precise, authoritative meaning of an entire programming language rested largely on the contents of one researcher's printed book. If a question arose about exactly how some particular feature was meant to behave in some unusual or ambiguous situation, there was, quite literally, no other higher authority to consult. Stroustrup later spoke about this period with a certain wry awareness of how strange and how much responsibility it placed on him personally, since every sentence in that book carried an outsized kind of weight, shaping how thousands of programmers around the world would eventually come to understand and use the language he had built. Through the mid to late 1980s, C++ continued to grow in capability and in adoption. In 1989, a significant update arrived, often referred to as C++ 2.0. This release added a meaningful set of further object-oriented features. It introduced multiple inheritance, which allows a single class to inherit characteristics and behaviors from more than one parent class simultaneously, a powerful but also famously tricky feature that can introduce subtle complications when, for instance, two different parent classes happen to define something with the same name. This release also brought abstract classes, a way of defining a class that establishes a kind of template or contract for related classes to follow, without itself being something you would ever create a direct, usable instance of. It added static member functions, which belong to an entire class as a whole, rather than to any one specific object created from that class. And it strengthened what is sometimes called const correctness, deepening the language's ability to enforce, at the level of the compiler itself, which pieces of data were genuinely meant to remain unchanging. 1990 brought another landmark publication, the Annotated C++ Reference Manual, often referred to by the shorthand ARM. This book was even more detailed and technically precise than the original 1985 book had been, and it would go on to serve as one of the most significant influences when the language was eventually formally standardized later in the decade. Also in 1990, an important commercial product entered the picture when the company Borland released Turbo C++. Turbo C++ became enormously popular, especially among students, hobbyists, and many professional programmers throughout the 1990s. It offered an accessible, relatively affordable, and notably fast compiler, paired with a friendly, text-based development environment that made writing, compiling, and testing programs feel more immediate and approachable than some of the alternatives available at the time. Turbo C++ also came bundled with a substantial collection of additional libraries, expanding what programmers could readily build without needing to write absolutely everything completely from scratch themselves. Even though its very last stable release came years later, in 2006, Turbo C++ left a lasting mark, and to this day, many programmers who learned to code in the 1990s or early 2000s have fond, specific memories of that particular software environment. It is worth pausing for a moment on just how important an inviting, friendly development environment can be to a language's wider adoption, separate entirely from the underlying merits of the language itself. A compiler that runs quickly, a development environment that feels responsive and approachable rather than intimidating, an editor that makes mistakes easy to find and fix. These qualities can shape an entire generation's first impressions of a programming language, just as powerfully as any feature of the language's underlying design. Turbo C++ offered exactly this kind of approachable entry point for an enormous number of people, many of whom were encountering serious, structured programming for the very first time, often as students sitting at a school or university computer lab, working through assignments late into the evening. Meanwhile, the original CalFront compiler, the one Stroustrup had so carefully designed and built in the early 1980s, continued to be refined through subsequent versions during this period. Interestingly, CalFront itself was written largely in C with classes and later in C++, which meant it was what is called a self-hosting compiler, a compiler capable of compiling itself using the very language it was designed to support. This is a satisfying, somewhat elegant kind of bootstrapping that recurs throughout the history of programming languages, a new tool eventually becoming sophisticated enough to build itself. However, CalFront could not continue forever as the primary reference implementation. As the language kept growing more sophisticated and ambitious, certain new features became extremely difficult to properly support within CFront's underlying architecture. One particularly significant example was the introduction of exception handling, a structured mechanism for managing errors and unusual conditions that arise while a program is running. Implementing exception handling required deep changes to how a compiler manages the underlying flow of a program and the lifetime of its data, and CFront's existing design simply was not well suited to accommodating this. Eventually, in 1993, C++ was retired, abandoned as the primary path forward, even as its historical influence on the wider implementation of C++ compilers and on the Unix software ecosystem, more broadly, remained considerable and lasting. Now, while all of this technical development was happening, a separate but equally important process had quietly begun, with C++ rapidly growing in popularity throughout businesses, universities, and a widening range of industries. A clear problem was emerging. There was still no single, official, vendor-neutral specification defining the language. Different compiler makers, naturally enough, had each made their own particular interpretations and decisions about ambiguous edge cases, which meant that code written for one compiler might not always behave identically or even compile successfully at all when fed into a different compiler. This fragmentation was a serious concern for an industry that was increasingly relying on this language for important, large-scale software projects, including operating systems, financial systems, and growing networking infrastructure. So an effort began to formally standardize C++. It started under the American National Standards Institute, commonly known by its initials, ANSI, beginning around 1989, and it later transitioned, beginning in 1991, to fall under the broader International Organization for Standardization, known by its initials, ISO. Bjarne Stroustrup was, naturally, a founding member of this standards committee, and remarkably, he remained an actively engaged member of it for decades afterward. For an extraordinary span of 24 years, he personally chaired a particular subgroup within the committee, the one responsible for carefully reviewing and managing proposals for new extensions to the language, a working group generally known as the Evolution Working Group. This standardization process took years of painstaking, deliberate, often quite technical debate among representatives from compiler vendors, large companies, academic institutions, and individual experts from many different countries. But the effort eventually bore fruit. In 1998, the very first official international standard for C++ was finally published, formally designated by the rather dry-sounding code ISO/IEC 14882:1998. Informally, and far more memorably, this standard became known simply as C++ 98. This first official standard brought enormous, lasting significance to the language. It included C++ templates, which allow programmers to write code in a way that works generically across many different data types, rather than needing to write essentially the same logic over and over again for each specific type individually. It formally incorporated exception handling, the very feature that had proven too difficult for the older compiler to properly support. It introduced namespaces, a tool that helps prevent naming collisions in larger projects by letting programmers group related names together under a kind of organizational umbrella, and significantly, it included something called the Standard Template Library, often abbreviated as the STL. The Standard Template Library deserves particular attention in this story, because its conceptual roots actually reach all the way back to 1979, around the very beginning of the language's history, even though it would not be folded into an official standard until nearly 2 decades later. The standard template library provided programmers with a rich, carefully designed and highly efficient collection of common data structures, like dynamic arrays, linked lists, and various kinds of maps and sets, along with a substantial collection of general-purpose algorithms for tasks like sorting, searching, and transforming data. By providing thoroughly tested, highly optimized, ready-made building blocks for these extremely common programming needs, the standard template library spared an enormous number of programmers from having to repeatedly reinvent these same fundamental tools from scratch, project after project, year after year. Its influence on how C++ programmers actually write code in practice has been absolutely profound, right up to the present day. After this first official standard was published in 1998, a period of refinement followed by 2003. The committee had gathered enough feedback and identified a sufficient number of issues and ambiguities in the original specification that they issued a revised version, generally known informally as C++03. This update did not introduce dramatic new features, so much as it cleaned up and clarified various technical details and corrected a number of defects that had been identified through years of real-world practical use. Then, in 2005, the committee released something called a technical report, informally nicknamed TR1. This document outlined a substantial collection of features that the committee was actively considering for inclusion in the next major version of the language. For a while, this anticipated next standard was given the informal placeholder nickname C++0x, reflecting an expectation that it would arrive sometime before the end of that decade, with the X serving as a kind of stand-in for whichever specific year it eventually landed on. As it turned out, the process took a bit longer than that early optimistic nickname had implied, but in 2011, this long-anticipated next major standard was finally completed and published, and it became known as C++11. And this particular release is widely regarded, by a great many experienced C++ programmers, as one of the single most transformative updates in the entire history of the language. It modernized C++ so substantially, in fact, that many programmers and writers in the field have described the language as splitting meaningfully into two distinct eras: everything that came before C++11 and everything that came afterward. C++11 introduced a remarkable number of significant features. It brought what are called smart pointers, which help programmers manage computer memory more safely and automatically, substantially reducing certain very common and historically troublesome categories of programming errors related to memory management that had plagued C and C++ programmers for decades beforehand. It introduced lambda expressions, which allow small, quick, unnamed functions to be defined directly in line, right at the exact point in the code where they are needed, rather than requiring a programmer to formally define and name a separate function elsewhere. It brought the auto keyword, letting the compiler automatically determine the appropriate data type of a variable based on the value being assigned to it, which can make code noticeably less verbose and repetitive in many everyday situations. It introduced range-based for loops, offering a considerably simpler, more readable way to iterate over the elements contained within a collection of data. And it added move semantics, a deep, somewhat technical but very impactful change that allows certain kinds of data to be efficiently transferred between different parts of a program without unnecessarily duplicating that data in memory, improving performance in many common scenarios. It is worth letting this particular moment in the story settle in a little more deeply, because of just how long the community had been waiting for it. More than 13 years had passed since the original 1998 standard. An entire new generation of programmers had, by this point, learned the language using the older, pre-standard rules as their starting point, never having known C++ any other way. When C++11 finally arrived, it did not simply add a few new conveniences around the edges. It meaningfully changed the everyday, line-by-line experience of writing the language, the small habits and patterns that programmers reach for instinctively, almost without thinking, dozens of times in every single file they write. Many programmers who lived through that transition have described it less like learning a handful of new commands, and more like rediscovering a language they thought they already knew quite well, only to find it suddenly capable of so much more than they had previously realized. Following this major C++11 release, the committee shifted toward a different, more predictable rhythm. Rather than allowing many years to pass between updates, They settled into a pattern of releasing a new standard roughly every 3 years, with each new release typically refining and building thoughtfully upon the substantial foundation that C++11 had established. C++14 arrived in 2014, functioning primarily as a smaller, more focused refinement of the many features that C++11 had introduced, fixing a handful of relatively minor issues and rough edges, and extending a few of the most useful and well-received new capabilities just a bit further. C++17 followed in 2017, bringing improvements that were generally aimed at boosting developer productivity and simplifying various common patterns that programmers had grown accustomed to writing repeatedly. Structured bindings were introduced in this particular release, offering programmers a more direct, expressive way to decompose a single combined object into a set of clearly separate, individually named variables, in one clean step. C++20 arrived in 2020, and it represented another genuinely major modernization milestone for the language, introducing several substantial new language and library improvements. Among its most significant additions were concepts, which give programmers a much more precise and expressive way to describe specific requirements that a generic piece of code expects whatever data type it is working with to satisfy, leading to considerably clearer compiler error messages when those particular requirements are not properly met. This release also brought modules, intended to offer an improved alternative to the much older, more traditional system of organizing source code that C++ had inherited directly from C, and it introduced coroutines, a powerful new tool for writing certain kinds of programs that need to pause and later resume their execution in a clean, structured, and far more manageable way than older approaches had typically allowed. C++23 followed in turn, continuing this established 3-year rhythm, and it was eventually ratified and formally published by the International Organization for Standardization in October of 2024, officially designated as ISO/IEC 14882:2024. This particular release focused heavily on usability improvements and meaningful enhancements to the language's accompanying standard library, continuing the broader pattern of steady refinement that had become characteristic of the language's standardization process in the years following the deeply transformative C++11 update. And now we arrive at the most recent chapter in this long unfolding story, one that has, remarkably, been unfolding right up through the very year we currently find ourselves in. Work on the subsequent standard, informally known throughout its development as C++26, had been progressing steadily for several years, moving through a careful, structured sequence of international standards committee meetings held in various cities around the world. The draft wording for this new standard was eventually judged feature complete, and it was sent out for a formal international comment ballot, the process by which national standards bodies from many different countries around the world get the opportunity to review proposed changes and raise any concerns or technical objections they might have. Following further discussion and the careful resolution of various ballot comments during a meeting held in Kona, Hawaii, in November of 2025, the committee continued refining the draft, and then, finally, at a meeting held in Croydon, London, in the United Kingdom, running from the 23rd through the 28th of March, in this very year, 2026, the International Standards Committee officially completed its technical work and formally shipped the C++26 standard. The vote to finalize it was not entirely unanimous, reflecting some genuinely sustained, thoughtful technical disagreement among committee members over certain specific new features, but it passed by a wide and decisive margin, and the committee's collective judgment was clear. The standard would move forward roughly as drafted. This new standard has been described by Herb Sutter, the chair of the International Standards Committee for C++, as quite possibly the most compelling release since C++11, echoing that earlier watershed moment from a decade and a half before. Among its most talked about new additions is compile time reflection, a substantial capability that allows code to be inspected and even generated automatically by the compiler itself before a program ever actually runs, rather than relying on mechanisms that only operate later, while a program is actively executing, the way reflection tends to work in several other, more dynamic programming languages. The standard also introduces a feature known as contracts, providing programmers with a formal, structured language-level way to specify preconditions and postconditions on functions, essentially clear, explicit, compiler-checked promises about what must be true before a particular function runs, and what is guaranteed to be true once it finishes, intended to help make C++ code meaningfully safer and more reliable overall, and reflecting a broader, sustained push across the wider C++ community toward improving memory safety. The new standard also includes various refinements addressing certain long-standing categories of undefined behavior, situations where, in earlier versions of the language, a program's behavior was technically left unspecified by the standard, often leading, in practice, to serious and sometimes quite difficult to track down bugs and security vulnerabilities. It is worth lingering a little longer on this particular moment, simply because of how unusually fresh it is within the story we are telling tonight. So much of the history we have walked through together happened decades ago, settled, documented, written about extensively by historians of computing and by Stroustrup himself. But this final chapter, the completion of C++ 26, happened only a matter of months before the night we are now sharing together. It is a small, quiet reminder that this is not simply a historical curiosity we are recounting, some closed chapter from a distant, finished past. It is a living, breathing, still actively unfolding story, with new pages still being carefully, deliberately written, even now, even this year, by people sitting in conference rooms in London, debating fine points of wording, with the same careful seriousness that Bjarne Stroustrup once brought to his earliest internal Bell Labs reports, all the way back in 1980. It is worth pausing here, gently, to reflect on just how unusual this entire journey has been. A language that began its life, all the way back in 1979, as a fairly modest little preprocessor, sitting quietly in front of an existing C compiler, intended to add just a few Simula-inspired organizational ideas to an already well-established and trusted systems language, has grown, gradually but steadily, decade after decade, into one of the most significant, most widely used, and most enduringly influential programming languages in the entire history of computing. Throughout all of these intervening decades, C++ found its way into an extraordinarily broad range of important applications across nearly every corner of the technology world. Major operating systems have relied on it extensively, with a very substantial portion of the Windows operating system, for instance, having long been written in C++. The game development industry adopted it enthusiastically and has remained deeply committed to it for many years, owing largely to the language's unusual and quite valuable combination of genuinely high performance, fine-grained control over computer hardware resources, and the higher-level, object-oriented organizational tools that help manage the sprawling complexity of modern game engines. Both of the two most widely used commercial game engines in the world, Unity and Unreal Engine, are built using C++ at their core, even though Unity also offers programmers the option to write their actual gameplay logic in a different, related language called C#. Beyond gaming, C++ has also become deeply embedded within the world of large-scale, high-performance computing systems. Major technology companies have relied on it for building critical infrastructure capable of processing truly enormous quantities of data efficiently. One well-known and widely referenced example is Google's MapReduce system, an influential piece of large-scale data processing technology that was originally built using C++. The language has also found a comfortable, lasting home in the financial industry, where the combination of speed, predictability, and precise low-level control that C++ offers has long proven valuable for the kind of demanding, performance-critical systems that underpin modern trading and financial infrastructure. It remains heavily used in embedded systems as well, the specialized, often resource-constrained software that quietly runs inside everyday devices, industrial equipment, and a wide variety of electronics. And it continues to be a foundational language for ongoing operating systems development, networking research, and various forms of formal software verification work. It is genuinely worth taking a slow, quiet moment here to consider why a language first designed all the way back in 1979 has managed to remain so deeply, persistently relevant, all the way through to today, in 2026, nearly half a century later. Bjarne Stroustrup himself has offered a fairly clear, characteristically grounded explanation for this longevity over the years. He has observed that C and C++ both became popular, in his own words, because they were flexible, relatively inexpensive to use, and considerably more efficient than many of the available alternatives at the time. He has also pointed out that C owed a great deal of its own early foundational popularity to the rapid, widespread adoption of the Unix operating system throughout the 1970s and into the 1980s, and in turn, C++ owed much of its own early popularity to its unusually high degree of practical compatibility with the existing, already widely used C language, which meant that the enormous population of programmers who already knew C and the vast, already existing libraries of working C code could be gradually, comfortably absorbed into this expanding new C++ ecosystem, rather than needing to be entirely discarded and replaced all at once. This question of compatibility runs as a steady, quiet thread throughout nearly this entire history, from the very earliest preprocessor approach used by CPRI, all the way through CPRUNT's deliberate strategy of translating its more advanced source code down into plain, ordinary, widely portable C, and continuing all the way up through the various modern standards we have walked through together this evening, an enduring, foundational commitment to remaining substantially compatible with C has consistently shaped the major decisions made throughout this language's long, evolving design history. This consistent commitment allowed an enormous, already established body of existing software and an equally enormous, already trained population of programmers to migrate toward this new language gradually, comfortably, and incrementally, rather than all at once, in some abrupt, disruptive, and far riskier technological leap. Bjarne Stroustrup has, over the years, written and spoken extensively about his own underlying motivations and design philosophy for C++, perhaps most clearly and memorably in a frequently quoted line where he explained that his initial aim for the language had been to create something where he personally could write programs that felt as elegant as the similar programs he had so admired as a student, while still remaining every bit as efficient, in practical terms, as the T programs that he and his colleagues already trusted and relied on every single day for serious, demanding work. That careful, deliberate balancing act between expressive, organized clarity on one side and raw, uncompromising performance on the other has remained the defining, central tension running quietly through nearly the entire subsequent history of this language's long, ongoing evolution. Stroustrup also documented his own underlying design philosophy at considerable length in a 1994 book titled The Design and Evolution of C++, and in a series of 3 substantial papers that he subsequently presented at the Association for Computing Machinery's History of Programming Languages conferences, gatherings specifically dedicated to carefully documenting and preserving the often surprisingly intricate, surprisingly human stories behind how major, influential programming languages actually came into being over time. Across his long career, Bjarne Stroustrup has personally authored or meaningfully contributed to well over 100 separate published papers concerning various aspects of C++, alongside numerous books on the subject, several of which have, over the years, been translated into more than 20 different languages for readers all around the world. Stroustrup's own professional journey continued to evolve steadily alongside the language he had originally created. After a T&T split into 2 separate companies in 1996, into a T&T itself, and a newly formed company called Lucent, Stroustrup chose to remain with a T&T, and he became a founding member of a T&T Labs, where he went on to lead their large-scale programming research department until 2002. He subsequently moved into academia, joining the computer science department at Texas A&M University, and he also spent more than a decade serving in a technical role at the financial firm Morgan Stanley, all while simultaneously holding a position as a visiting professor at Columbia University in New York. Since 2022, he has held a full, permanent professorship at Columbia. Across the years, his substantial body of work and his lasting contributions to the field have been recognized with a wide range of significant honors, including the Association for Computing Machinery's prestigious Grace Hopper Award, formal election to the National Academy of Engineering, the distinction of being named a Fellow of the Institute of Electrical and Electronics Engineers, and in 2018, he was honored with the Charles Stark Draper Prize, awarded by the United States National Academy of Engineering. specifically recognizing his foundational work in originally conceptualizing and subsequently developing the C++ programming language. There is something quietly satisfying in noticing the shape of this career taken as a whole, moving from a research lab to a renamed corporate research division, into a university computer science department, into the deeply practical, fast-moving world of financial technology, and eventually settling back into academia once more at Columbia, all while never once fully stepping away from active, ongoing involvement with the International Standards Committee, responsible for the language he had first sketched out as a young researcher, decades before. Very few people in any technical field maintain such a long, continuous, hands-on relationship with a single piece of work across the better part of 50 years, watching it grow, adapt, occasionally stumble, and continue evolving, long after most original creators of most technologies have moved entirely on to other things. Before we drift onward into the more recent decades of this story, it is worth resting for a while longer on the deeper currents that were moving underneath the C++ world throughout the 1990s, because that decade in particular was a slow, eventful, and quietly formative period for the language, even before the first official standard arrived in 1998. Through the early 1990s, as C++ spread further beyond Bell Labs and into universities, research institutions, and a fast-growing software industry, a number of different compiler vendors began building their own independent implementations. This was, in many ways, a healthy sign of a language gaining real traction in the world, but it also introduced a slow, creeping kind of fragmentation. One compiler vendor might interpret some particular subtle rule slightly differently from another. A program that compiled cleanly, using one company's tools, might behave unexpectedly, or fail to compile at all, when handed to a different company's compiler. For a language that was increasingly being trusted with serious, large-scale, commercially important software, this kind of inconsistency was a real and growing concern, and it was one of the strongest underlying motivations driving the long, patient standardization effort that we touched on earlier. During this same period, a great deal of practical, real-world experience was also quietly accumulating about how object-oriented programming actually worked in practice, at scale, across large teams and large code bases, as opposed to how it had looked on paper, in smaller academic examples. Programmers discovered that some of the more ambitious ideas, like deeply layered, elaborate class hierarchies, built many levels deep, often introduced more complexity and confusion than they resolved. This period of hands-on, often humbling experience shaped a great deal of the more measured, practical design thinking that would later influence both the 1998 standard and the years that followed it. Bjarne Stroustrup himself, in his writings from this era, was notably cautious about treating object orientation as some kind of universal solution to every programming problem. He wrote and spoke at length about the idea that C++ was never meant to be purely or exclusively an object-oriented language in the strictest theoretical sense, but rather a practical, multi-paradigm tool, one that allowed programmers to freely mix procedural styles inherited from C, object-oriented styles inspired by Simula, and eventually, increasingly, generic and functional styles as well, choosing whichever approach best suited a given problem, rather than being forced into a single rigid philosophy. This multi-paradigm flexibility is, in fact, one of the quieter but more important threads running through the entire history we have been following tonight. Unlike some programming languages that were designed from the very beginning around one single, fairly strict philosophy, C++ grew, gradually and somewhat organically, into a language that could comfortably support several quite different styles of thinking about a problem, all within the same code base, even within the very same function, if a programmer chose to mix them. This flexibility has sometimes been described, even by people who deeply admire the language, as a kind of double-edged quality. It gives experienced programmers an unusually wide and powerful toolbox to reach into, but that same breadth of choice has also, at times, made the language feel large and challenging for newcomers first arriving and trying to get their footing. Templates, which we touched on earlier as part of the 1998 standard, deserve a slightly closer, slower look here, because their story is itself a quiet, interesting thread within the larger history. The fundamental idea behind templates is to let a programmer write a single piece of logic, say a function for sorting a collection of items, or a structure for storing a list of values in a way that does not commit in advance to any one specific data type. The same template might then be used to sort a collection of whole numbers, or a collection of decimal numbers, or a collection of pieces of text, with the compiler automatically generating the appropriate, specifically tailored version of that code for whichever particular type is actually being used at the moment the program is built. This idea, often referred to as generic programming, turned out to have consequences that went considerably further than anyone fully anticipated at the outset. Researchers and practitioners gradually discovered that the template system, originally intended simply as a tool for writing reusable, type-flexible code, was, almost as a side effect, powerful enough to perform entire calculations and logical decisions during the compilation process itself, before a program had even begun running. This discovery led to an entire, somewhat unusual subfield within C++ programming, often called template metaprogramming, where programmers learned to use the compiler itself as a kind of calculating engine, computing certain results in advance, baked permanently into the final compiled program, rather than calculating them freshly each time the program actually ran. This was, by most accounts, a genuinely unplanned, emergent capability, discovered gradually by curious, persistent programmers, experimenting with the boundaries of what templates could do, rather than something that had been carefully, deliberately architected from the very beginning. There is something quietly poetic in this particular story, a feature designed for one specific, fairly modest purpose, writing reusable code across different data types, turning out, almost by accident, to unlock an entirely different and far more ambitious capability that nobody had originally set out to build. This pattern, where a carefully designed feature reveals hidden depths only after years of patient, curious experimentation by a wide community of users, recurs throughout the history of programming languages more broadly, and it stands as a quiet reminder that even the most careful, deliberate design choices can carry consequences that ripple outward in ways their original designers never fully anticipated. Let us also slow down for a moment and think about the wider competitive landscape that C++ found itself growing up alongside, because no programming language exists or evolves in complete isolation. Throughout the 1990s, a language called Java emerged, developed at Sun Microsystems, drawing very visible, very deliberate inspiration from C++ in terms of its surface-level syntax, while making quite different underlying design choices, particularly around automatic memory management and a more restricted, more tightly controlled approach to certain features that C++ had left more open and flexible. Java's rise introduced, for the first time, a serious, widely adopted alternative in many of the application domains where C++ had previously held a fairly unchallenged position, especially in general-purpose business software and large-scale enterprise systems. Rather than this competition diminishing C++, it arguably helped clarify, over time, where C++'s particular strengths most clearly and durably lay: in systems programming, in performance-critical applications, in games, in embedded devices, in any setting where direct, fine-grained control over computer hardware and memory genuinely mattered, and where the overhead introduced by more automatically managed languages was something a development team could not comfortably afford. Later, in the 2000s and beyond, other languages would emerge and carve out their own particular niches as well. Languages like C#, developed at Microsoft, and later, Rust, developed initially at Mozilla, each making their own distinct trade-offs around safety, performance, and ease of use. Rust, in particular, has often been discussed, especially in more recent years, as offering many of C++'s performance advantages while attempting to eliminate, through a different, more restrictive underlying design, several entire categories of memory-related bugs that have, historically, been a persistent and sometimes serious source of software vulnerabilities in C and C++ programs over many decades. This ongoing, broader industry conversation around memory safety has, in fact, directly and visibly shaped some of C++'s own more recent standardization efforts, including several of the safety-focused refinements that found their way into the recently completed C++ 26 standard that we discussed a little earlier this evening. It is interesting, too, to notice how Python, an entirely different kind of language altogether, designed with a strong emphasis on readability and a more relaxed, interpreted style of execution came to occupy yet another corner of the wider programming landscape during these same decades, frequently used for quick scripting, for data analysis, and for the early stages of new software projects, while C++ continued to be reached for whenever a project's performance requirements grew demanding enough to justify the additional complexity. In many real-world organizations today, several of these languages coexist comfortably within the very same company, even within the very same overall software system, each one handling the particular part of the problem it happens to be best suited for. A quiet, practical division of labor that has become increasingly common as software systems have grown larger and more layered over the decades. It is also worth pausing to remember the sheer number of people spread across so many different countries who have quietly devoted meaningful portions of their professional and even personal lives to this one language over the years. Beyond Bjarne Stroustrup himself, the long history of C++ is dotted with other names that, while perhaps less universally well known outside specialist programming circles, made genuinely lasting, significant contributions. Andrew Koenig, a longtime colleague of Stroustrup's at Bell Labs, contributed extensively to the language's early design discussions, and later became deeply involved in the international standardization process itself. Alexander Stepanov, working at Hewlett-Packard, was the principal designer behind the standard template library that we discussed earlier, the rich collection of containers and algorithms that became such a central, foundational part of the 1998 standard, and that remains, to this day, one of the most heavily used parts of the entire language. Herb Sutter, whom we mentioned earlier in connection with the very recent C++26 standard, has, for many years, served in various significant leadership roles within the International Standards Committee, and has written and spoken extensively, helping translate often quite technical, abstract committee discussions into guidance that working programmers around the world could more readily understand and apply in their own day-to-day projects. Beyond these few names, there have been thousands of other contributors over the decades, compiler engineers working quietly at companies large and small, academic researchers publishing careful papers analyzing particular language features, authors writing textbooks and tutorials that introduced new generations of students to the language, and ordinary working programmers who, encountering some particular rough edge or limitation in their daily work, took the time to write up a formal proposal and bring it patiently before the Standards Committee, sometimes waiting years to see whether their idea would eventually be adopted. The history of C++, in this sense, is not really the story of one person, even though Bjarne Stroustrup's foundational role remains absolutely central and irreplaceable. It is, more accurately, the story of an enormous, sprawling, multi-generational collaboration, one that has, by now, outlasted the active careers of many of its earliest contributors, even as new contributors continue to join its ranks every single year. The Standards Committee meetings themselves, which we touched on briefly before, have their own quiet, recurring rhythm worth sitting with for a moment. Twice each year, typically, representatives travel to a different host city, sometimes in North America, sometimes in Europe, occasionally elsewhere around the world, for a week of long, often quite technical, sometimes genuinely contentious discussions, working through proposed papers, debating fine points of wording, considering how a proposed new feature might interact, sometimes in surprising and unwelcome ways, with features that already exist elsewhere in this large, sprawling language. Recent meetings, as we noted, have drawn well over 200 participants, some attending in person, and many more joining remotely, representing national standards bodies from dozens of countries, alongside engineers from major technology companies, academic researchers, and a number of independent consultants and trainers who have built entire careers around their deep, specialized expertise in this one particular language. It is, in its own quiet way, an enormous, sustained, largely volunteer-driven act of collective stewardship, carried out patiently, meeting after meeting, year after year, by people who believe, evidently quite deeply, that getting these careful technical details right actually matters for the millions of programmers and the uncountable software systems that will eventually depend on whatever decisions they ultimately settle upon. The process by which a new feature actually makes its way into the language is, itself, a slow and carefully structured one, worth describing gently here. Someone, often a working programmer who has personally run into some particular limitation, writes up a formal proposal paper, describing the problem clearly and outlining a specific suggested solution, including the exact wording that would need to be added to or changed within the existing standard. That paper is then presented, often more than once, to a relevant subgroup of the committee, where it receives detailed, sometimes quite skeptical scrutiny. Revisions follow, sometimes many rounds of them, each one incorporating feedback gathered from the previous round. Only once a proposal has survived this extended, iterative process of refinement does it move toward a vote in front of the full committee, and even then, it must typically clear that vote by a substantial, convincing margin before being folded into the working draft of whatever standard is currently under development. A single feature can sometimes take many years, occasionally even a full decade or more, moving slowly through this careful, deliberate process before it finally becomes a permanent, official part of the language that ordinary programmers around the world can rely upon. It is also worth gently noting just how broad the educational and cultural footprint of C++ has become over the decades. Countless university computer science programs around the world have used C++ at one point or another as a primary teaching language, precisely because its multi-paradigm nature, combining procedural, object-oriented, and generic programming styles all in one place, gives students a genuinely broad, practically useful foundation, even if that same breadth can make the language feel, especially at first, somewhat more demanding to learn thoroughly than some more narrowly focused alternatives. Competitive programming, a popular activity among students and enthusiasts that involves solving carefully designed algorithmic puzzles under strict time limits, has also long leaned heavily on C++, owing largely to its unusually favorable combination of raw execution speed and a sufficiently expressive, sufficiently high-level set of tools, allowing contestants to write reasonably clear, reasonably quick to produce code that still runs about as fast as the underlying hardware will realistically allow. Beyond formal university classrooms, an enormous, informal ecosystem of textbooks, online tutorials, video courses, and community forums has grown up around C++ over the decades, helping pass the language along from one generation of self-taught programmers to the next. Some of the earliest and most influential of these textbooks were written by Stroustrup himself, but many others followed, written by educators and practitioners who each brought their own particular teaching style and their own particular emphasis to the task of explaining this large, sometimes intimidating language in a way that felt approachable and learnable, rather than overwhelming, to someone encountering it for the very first time. It is worth slowing down even further here to sit with the question of why object-oriented programming, the core idea Stroustrup borrowed from Simula, all the way back at the very start of this story, turned out to matter so much to the software industry, not just within C++, but far more broadly. Before this style of thinking became widespread, a great deal of software was written in what is generally called a procedural style, where a program is organized primarily as a sequence of steps, with data sitting somewhat separately from the functions that operate on it. This approach works perfectly well for smaller programs, but as software projects grew larger, as teams of programmers grew bigger, and as projects were expected to be maintained and extended over years rather than months, this looser separation between data and behavior started to create real, practical difficulties. It became harder to reason about which parts of a sprawling program were allowed to modify which particular pieces of data, harder to isolate the source of a bug, harder for a new programmer joining an existing team to quickly build an accurate mental picture of how all the different pieces fit together. Object-oriented programming offered a different, more contained way of organizing all of this complexity by bundling related data and behavior together into a single class, and by carefully controlling which parts of that data were exposed to the outside world and which parts remained safely hidden away inside, a concept generally referred to as encapsulation. Programmers gained a powerful tool for managing growing complexity. A large program could be conceptually broken down into a collection of smaller, more self-contained, more independently understandable pieces, each one responsible for its own particular slice of behavior, communicating with other pieces through carefully defined, deliberately narrow interfaces, rather than everything reaching in and touching everything else's internal data directly. This was the deeper, more practical promise that drew Stroustrup to Simula in the first place. And it was this same promise that motivated him to spend so much careful effort trying to bring a version of these ideas into the considerably faster, more hardware-adjacent world of C. It is also worth pausing, gently, on the printed books and manuals themselves, because in an era before the internet had become the default way that programmers learned new tools, these physical documents played an unusually central, almost irreplaceable role in spreading knowledge of this new language around the world. The original 1985 edition of the C++ programming language was, by most accounts, a relatively compact volume compared to later editions, but it nonetheless served, for years, as the closest thing the world had to an authoritative, complete description of how the language was actually meant to behave. Programmers in those years would often work with the book open beside their keyboard, checking carefully against its examples and explanations as they wrote and debugged their own code. Later editions of the same book grew substantially larger and more thorough, eventually running to well over 1,000 pages by the time later versions, covering the modernized post-2011 language, were published. The 1989 Annotated Reference Manual, which we discussed earlier, took this even further, offering an unusually detailed, carefully annotated walk through the language's precise rules, written specifically with compiler implementers and serious language specialists in mind, rather than newcomers simply trying to learn the basics for the first time. These books, taken together across the decades, quietly trained an enormous number of the programmers who would go on to build much of the software infrastructure the world now depends upon. It is interesting, too, to sit with the sheer variety of hardware and computing environments that C++ has, over its long history, found itself running on. In the 1980s and into the 1990s, this meant a wide range of Unix workstations, increasingly powerful personal computers, running early versions of Windows, and a whole ecosystem of specialized scientific and engineering computing systems. As the decades passed, this same language found its way into video game consoles, into the deeply embedded processors controlling everything from automobiles to medical devices to industrial machinery, into the servers quietly powering large portions of the internet, and eventually into the kind of massive, distributed, planet-scale computing infrastructure operated by the largest technology companies in the world. Very few programming languages from this same era, the late 1970s and early 1980s, have managed to remain genuinely relevant, genuinely actively used and actively developed, across such an enormously wide and continually shifting range of computing environments, for such a long, sustained stretch of time. It is worth dwelling for just a little longer on how unusual this particular kind of versatility really is. Most technologies, even quite successful ones, tend to be closely associated with one particular era, one particular kind of hardware, one particular dominant use case. But C++ has, somewhat remarkably, managed to remain a genuinely sensible, practical choice across an extraordinary range of very different contexts, from the tightly resource-constrained microcontroller inside a household appliance to the enormous, sprawling distributed server clusters that power the largest websites and online services in the world. This kind of sustained, cross-generational versatility is rare, and it speaks, in its own quiet way, to just how carefully the original underlying design balanced performance, portability, and expressive power all those decades ago. And there is something quietly remarkable, too, in simply noticing how many different, distinct generations of programmers this one language has now passed through. Someone who first learned C++ in the 1980s, working directly with C-Front and the very earliest printed reference manuals, experienced a meaningfully different language than someone who first learned it in the late 1990s, just after the first official standard had been published, who in turn experienced a meaningfully different language than someone learning it today, in 2026, with templates, smart pointers, lambda expressions, concepts, modules, and now compile-time reflection, all readily available as familiar, well-established parts of the modern language's everyday toolkit. And yet, running quietly underneath all of these successive generations and all of these accumulated layers of new capability, a great deal of the original 1979 vision still remains, clearly, recognizably present, a language that tries, carefully and deliberately, to combine genuine expressive elegance with genuine, uncompromising, hardware-level performance, refusing, across nearly 5 decades now, to fully give up on either one of those two original, sometimes competing goals. It is also worth taking just a moment to gently appreciate the sheer scale, the genuine reach, of what this particular piece of careful, patient engineering eventually grew into. When Bjarne Stroustrup first sat down in 1979 to begin sketching out the earliest ideas behind C with classes, he was, by his own later account, essentially just told by his managers at Bell Labs to go find something interesting to work on, a wonderfully open-ended, almost casual-sounding instruction by today's standards, that nonetheless ultimately led, through years of careful, often quite unglamorous engineering work, to a programming language that would eventually help power major operating systems, ambitious and immersive video games played by hundreds of millions of people worldwide, demanding high-frequency financial trading systems and enormous, planet-scale data processing infrastructure operated by some of the largest and most influential technology company in the world. And even now, all these decades later, in 2026, the language continues to actively evolve. The recently finalized C++26 standard is already looking thoughtfully ahead toward its own eventual successor, informally referred to, even now, as C++29, with very early exploratory work already quietly underway on some of the ideas and proposals that may, in time, eventually shape that future release as well. Compiler makers around the world, including the widely used free and open source GCC compiler, along with various other compiler vendors, continue steadily implementing experimental support for these very newest features, often well before a given standard is even formally finalized and published, allowing programmers and software teams around the world to begin carefully experimenting with emerging capabilities long before those capabilities become an official, permanent part of the broader language specification. The C++ Standards Committee itself remains a remarkably large, remarkably active, and genuinely global undertaking, even after all of these years. Recent standardization meetings have regularly drawn well over 200 participants from dozens of different countries around the world, some attending entirely in person, gathering together in a different host city roughly twice each year, and many others joining these lengthy, technically detailed meetings remotely online. This entire process represents an enormous, sustained, ongoing, largely volunteer-driven collaborative effort, carried out year after year by people who, in a great many cases, are not specifically paid for this particular standards-related work, but who nonetheless choose, again and again, to dedicate countless hours of their own personal time toward the very deliberate, very careful task of thoughtfully shaping the future of a programming language that, by this point, quietly underlies an absolutely enormous portion of the world's critical digital infrastructure. It is a genuinely remarkable thing, when you stop to think about it slowly and quietly, the way a single, focused idea, one researcher's relatively modest, practical attempt to gently and thoughtfully combine the very best, most useful qualities of two rather different programming languages, similar on one side and C on the other, eventually grew, year after year, decade after decade, into a sprawling, truly global, multi-generational collaborative effort. Thousands of programmers, across more than 4.5 decades now, have each contributed their own particular insights, their own carefully considered critiques, their own thoughtfully proposed extensions, gradually and patiently shaping and reshaping this language, one careful, deliberate standard at a time, into the rich, capable, and still actively, visibly evolving tool that so many software systems around the world continue to quietly depend upon today. There is a kind of patience embedded in this entire story that feels worth sitting with quietly, here near the end. Nothing about this language's long history happened quickly. Nothing about it happened through some single, dramatic breakthrough moment. It happened, instead, through an accumulation of small, careful, often quite unglamorous decisions, made one at a time, across nearly 5 decades, by people who were, for the most part, simply trying patiently to solve real, practical problems they personally encountered in their own work. That quiet, unglamorous, deeply collaborative patience is, in its own way, just as remarkable a story as any single dramatic invention could ever be. And that, gently, slowly, brings us to the natural close of this particular story, at least for tonight. From a small, unassuming research preprocessor called CPRE, built quietly inside a research lab in New Jersey back in 1979, all the way through Seafront, through C with classes, through that small but lasting naming decision in 1983, through the foundational 1998 standard, through the genuinely transformative C++11 release, and onward, through the steady, predictable 3-year rhythm of C++14, C++17, C++20, and C++23, and finally arriving at the freshly completed C++26 standard that the International Committee only just finished shipping this past spring, in March of this very year. It has been, by any reasonable measure, an extraordinarily long, an extraordinarily patient, and an extraordinarily collaborative journey. If you are still here with me, still listening quietly in the dark, then you have made it all the way through. There is nothing more you need to take in tonight. Let your thoughts soften now. Let this story settle quietly into the background, and let yourself drift, slowly, gently, into sleep.